Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Hopefully, you guys are doing great. Had a good long 3-day weekend. Had a good Valentine's Day. I had a good Valentine's Day. I'll tell you guys about it in a bit. Don't worry, I don't kiss and tell. That's not what it's about. But I guess I will start by telling you guys some good news. But I should start with some bad news, actually. So my migraine is acting up today, so I'm kind of, not at 100%. So that's going to explain why I'm not as excited about the good news. The good news is on Valentine's Day, my brother had his first kid. So now you guys all have to call me Uncle Jhevon. And very excited about it, even though I don't seem like it because the headache. I should probably actually just look excited for the thumbnail or something. So that was good. It was a good Valentine's Day. So yeah. Great things are happening. Hope you guys had a good time as well. Apparently, Kathleen is the only one here. Where's everyone else? I don't know. Remember, we're not about into being shy. Come out of your shell, guys. Let me see you. Come on. Good. Thank you. Thank you. Fight it. Fight it. Fight it. Thanks for the congratulations, Stephen. But yes, engaging in your online class is very important. Trust me. Just you need to show up, show your face. Try to participate. Today, we have a very important thing to talk about. Essentially, I'm going to do one example, but I'm really going to elaborate on it. Other than that, I'm going to motivate the lead up to that example. And yeah, I'll leave another example for you guys to try for tomorrow, but that's essentially where we're going. Do I remember what we're doing now? Yes, I do, because I did it in the class before. So let's actually get into it. Share my screen. Let's share my screen. Okay, there we go. Looking good. Make sure I can see the chat. Thanks for the congrats, Tommy. Okay. All right, let's get the show on the road. We're already starting a few minutes late. So today we're going to start with story time, right? So so that's what we're going to do in celebration of the momentous occasion. You don't have to take this too seriously. You don't even have to take notes at this point if you want. I just thought I would motivate some things by just leading you to a nice discussion. Story time, baby Gauss. And adding the first 1,000 numbers. So definitely very famous guy in math circles, very famous mathematician, very prolific. We owe a lot to him, especially in the realm of complex analysis and physics also, and chemistry, I guess. He was amazing, right? So there was this German mathematician called Carl Friedrich Gauss. A lot of mathematicians, very revered. He's up there with Euler and those other dudes, right? So legend has it, don't know if this story is true, but I've heard the story so many times, it might as well be true now. When Gauss was very young, little itty bitty baby, 4 years old, 5 years old, was in, daycare class with, the rest of his friends. Kids at this age were just learning how to count things with pebbles and physical objects. They didn't know negative numbers exist. Gauss was actually pretty good at algebra and arithmetic by this point. On one day, class was being specifically rowdy. Teacher had enough, so she was like, "Everybody, sit down, be quiet. I wanted you all to add the numbers from 1 to 1,000." Right? So these are a bunch of young kids. They barely know how to count on their fingers, and some of them probably don't even know how to count all the way to 1,000. But she's like, "Okay, this will keep them busy for like forever." So it'll definitely keep them busy until the end of the day. So you have these little kids there, 1 + 2 + 3, counting with their pebbles, trying to count up to 1,000, right? A couple minutes later, baby Gauss walks up to the teacher's desk. Boom, here's the answer. 500,500. And she's like, what? How did he, like, even if he could count to 1,000, adding all the numbers up to 1,000 should have taken you longer than this. But it didn't, because baby Gauss was clever. And here's what baby Gauss did. So baby Gauss was like, okay, very good at abstract thinking at 4 years old, obviously. He's like, okay, here are the numbers that I want to add up. Of course, he used ellipses. I believe it. Right? He called this S. He also knew that addition was commutative. So he's like, you know what? Here's something that he also noticed. It's the same as if you add the numbers in the opposite order. Of course, right? Yeah, that's the same. Now here's something else he noticed. If I were to add these numbers in a column, something interesting happens. See, here you have 1,001, 1,000 plus 1, right? Now you take 999 plus 2, what do you get? Well, you get 1,001 actually. 998 plus 3, what do you get? 1,001 again. And no, this repeated the whole way down. Right? You get a bunch of 1,001s. Now, of course, because he added these two, this isn't the thing that he actually wanted. This was actually double what he actually wanted. So that's what 2s would look like. However, because you have the same number repeated, and he knew it repeated 1,000 times because it's lining up with the columns labeled 1 to 1,000, this is 1,000 1,001s. That is double what he wants. So obviously the thing he wants is going to be 1,000 times 1,001 all over 2. Now, of course, you can cancel because you can cancel cross multiplication, and this will leave you with 500. So now that's it, 500 times 1,001. Then you do that with multiplication. Knowing your multiplication tables, you get 500, 500. That's, if you were to sit down, add all the numbers from 1 to 1,000, all the whole numbers, that's how much you would end up with, 500,500. And baby Gauss figured this out. Very, very cool. Now here's something else, throwback to high school. Some of you might go back to a dark place, but just relax. It's from the fun part of high school, math class, right? So there was something called, you may recall, a geometric series. So-called because of its connection to the geometric mean, but whatever, right? A geometric sequence was just a list of numbers that followed a certain pattern. You started with a number, and then you multiply that number by some other number, r, and then you keep doing this. So I multiply by r again, then I multiply by r again, then, and I keep doing this, right? And I do this so that at the end of the day, I have n numbers. So I started out with a, that was the first number. Then I multiply by r n minus 1 times. So I have a list of n numbers here. And the series is when we add all these numbers together. So you add all these numbers together. Now, how do we actually calculate this? Well, it turns out we can use the same trick that baby Gauss used. We can call this something. It's just going to add up to some number s. And we're going to modify the trick a little bit. What we're going to do is we're going to take that thing, that entire line, and multiply through by r, right? So if I take a times r, I get ar. If I take ar times r, I get ar squared, ar cubed, ar to the 4th, plus dot, dot, dot. I'm going to get, this guy's going to be ar to the n minus 1. This guy's going to be ar to the n. And again, we're going to do that addition trick. Well, more specifically, we're modifying this. We're going to actually do a subtraction trick. We actually want to cut down the number of things we have. And that's why we multiply by r. So if this was line 1, that's line 2. What I'm going to want to do now is take line 1 and subtract line 2. And so what we're going to have is on the left side, we have s minus rs. What happens on the right side? Well, notice that I actually recreated a huge chunk of the original series. These guys would cancel AR minus AR squared minus AR squared, blah, blah, blah. This keeps going until, you know, this guy gets canceled with the guy before, that guy gets canceled with the guy before. This guy, of course, is going to get multiplied by a -1 when I subtract it. And so this all ends up being A minus AR to the N. Interesting. Okay, so now what we can do, factor out the common S on the right side, factor out the A on the left side. I blame my mind brain. Okay, factor out the A on the right side, and then I can solve for S by dividing. Okay, so that is actually the sum of a geometric series, right? Interesting, right? Now, you don't have to memorize this formula just yet. It is going to lead into something that I want us to talk about. So here's something that I want you to notice about a geometric series. Remember when we were doing compound interest and we were trying to figure out the formula for compound interest, and what we were doing was we just kept adding the what we had before to the new value every time. And notice what was happening every time. Like we started with $1,000. We hit it with compound interest, which amounts to multiplying it by 1 plus R over N. We hit it with compound interest again, which hit that with 1 plus R over N. So it became 1 plus R over N squared, then 1 plus R over N cubed, 1 plus R over N, blah, blah, blah. And then we combine this and realize, oh, the compound interest formula is 1,000 times 1 plus R over N to the M amount of times, where that was N times T, right? The number of times compounded, right? And so that's what we figured out. I want you to notice that what we actually did there to figure out that formula was a geometric series. That is what it actually looked like, right? Think of my A as the $1,000 and my little r as the 1 plus R over N. You get this, right? And that's important for another reason, which is what we're going to talk about. So now what I want us to do now, let's make what we've been doing more realistic with repeated payments. Okay, so I mean, what we've been doing so far is important, but obviously not very realistic. Who walks into a bank, says here, gives them $1,000 and disappears for years on end and then shows up out of the blue? How much do I have now? Like nobody, right? Like no one goes to a bank once in their life. We deposit money into a bank every month or every 2 weeks, usually when we get paid, right? So we repeatedly do payments, right? So if we don't have a model for repeated payments, what use is the math, right? We need to have this idea of, I'm not just putting in $1,000 and forget about it like it's a George Foreman grill. I'm going to put in $1,000 every month. Every month, you're going to see me come and put $1,000, right? Now, at the end of the day, I want to know how much total money do I have, right? But if the account is growing with compound interest, it's not just growing by multiples of 1,000. It's growing like this, because at the end of every month, it gets hit by interest. So every time when I put in A dollars 1 month, it becomes A times R dollars the next month, and then A times R squared dollars the next month, and so on, right? And so I want to know how to model that situation. I'm making repeated payments. Now, the fancy word for repeated payments in finance, because finance people always make up fancy words for very simple ideas, because I'll rant about this at the end of the class, so don't worry about this. Finance people want you to think that you really, really need them, so they make it sound complicated, like, okay, whatever, I'll pay you to deal with this for me. And I'm going to show you how that can cost you by the end of today's class. But this repeated payments is called an annuity. So let's actually talk about that. This leads to what we're covering today is section 3.3, future values of annuity. Future value of annuities. We're not going to touch on it today, but I'll leave an example for you to try tomorrow about something called a sinking fund. Future values of annuities. What's an annuity? Let's actually make sure we know that. Definition: an annuity is a sequence of regular payments. That's all it is. Now, there are situations in which this payment is being made to you. So usually when people talk about annuities, that's what they're talking about. It's some kind of account that pays them every month in retirement. So they get a sequence of payments even though they're not working. So it's called annuities. So if you're doing retirement planning with someone, they'll throw around this word a lot. But that's all it is, a sequence of regular payments. This is time-wise. So like every month, every week, something very predictable and very evenly spaced. That's all an annuity is. Now, there's a very special type of annuity that I want to talk about in this class. There are many kinds, but we are going to focus on one. If the payments are all of, oh, by the way, if I didn't say it, like now it's go time. We should be serious. You should be taking notes at this point, right? You didn't have to take notes at story time or even follow that argument completely. I just wanted you to know that what I'm about to talk about doesn't just come out of the blue, okay? But now, like it's like, pay attention, perk up, probably turn on your videos again, and be ready to talk to me. Have your calculators handy because I'm going to ask you to compute stuff. If the payments are all of the same size, so it gets complicated if you're depositing a different amount every month. Like today, I deposited $1,000. Tomorrow, next week, 953, and then another, right? Just assume that we're making even payments here. You're doing something like dollar cost averaging when you're investing. The same size, and interest is applied at the end of the pay period. It is called an ordinary annuity. So that's what's called an ordinary annuity. Note, in this class, we'll only talk about ordinary annuities. So just a heads up there. So from now on, every time you hear me say annuity, I really mean ordinary annuity, but I'm not going to say the ordinary all the time. So when I say annuity, I really mean ordinary annuity, but there are more kinds of annuities. Okay, so let's actually figure out how these guys work, how we're going to be able to predict how our annuities are growing in the market or with interest or whatever. So here's what we're going to do. Let R be the regular payments you're making. T number of years you're doing this for. N number of times compounded per year. I want M to be, well, I'm going to define this to be the product NT, and this is just the number of periods, really. So it's compounded 12 times per year. Then in 2 years, you would have had compounding 24 times, right? Which is n times t. I'm using m to do that. We'll change the notation later, but for now, because I'm going to write stuff out and derive stuff, do a little mathy stuff, I don't want to have to be writing out a lot of variables. Let R be the interest rate. APR. Okay. So here's what we're going to do. And again, you don't have to know how to derive this. I just want you to know that the formulas I'm going to come up with don't come out of thin air. You're just going to have some notion of where this comes from. So let's look at the time period. Let's say this is now, right? And this is period 1, period 2, period 3, right? And this is going da da da. Period m minus 1. Maybe I'll write out the first one. You know, that stands for period. And the period here can be anything, but a lot of times for us, it's going to be months, right? Or whatever I tell you. And period m, right? At the end, when I want to actually figure out how much money do I have now, right? So what we're going to do is we're going to pretend we're making payments at each period. So here's payments that I'm making. I put in a regular sum of money, R, at all these periods, right? So these are my payments. Okay. Now what I want to do is I want to track the value of these payments in the future. So what I'm going to do is track the future value of payments. This is, of course, going to be abbreviated FV. So now, because it's an ordinary annuity, I know that I get hit with interest at the end of the period. So what does that mean? If I'm making this investment for M periods, then the very first thing that I put into the account actually gets hit with interest M minus 1 times, because it doesn't get hit with interest in the first period. It gets hit with interest at the end of the first period, going into the second period. So this first sum of money that I put in, he's going to get hit with interest, which we know looks like that when it's compounded, M minus 1 times. The second payment I put in is going to get hit with interest, M minus 2 times. The third payment is going to get hit with interest, M minus 3 times, and so on and so forth. The second to last payment I put in gets hit with interest 1 time because it gets hit with interest going into the next period. And then this last amount of money that I put in doesn't get hit with interest at all, right? Because technically he would get hit with interest in the M plus first period, but we're stopping things at the M as in mama period. Okay, so now what do we want to do? We want to know how much money we have in the account. So we're going to add up all these guys. So FV, the future value in the account, this is going to be the sum of the future values above. Now, what is that? Well, I'm going to add it in the opposite order just to kind of make the connection with story time. So let's say I added backwards R, then I add R times 1 plus R to the N. Then I add R times 1 plus R over N squared plus dot, 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 dot. Okay, keep going. 1 plus R over N to the M minus 2 plus 1 plus R over N to the M minus 1. Now, what you should notice here is gasp. Now, everyone noticed that. This is a geometric series. Okay. Notice that that actually looks like what we're talking about earlier up here with the ARs, right? If I replace my A with big R and replace my little r with parentheses 1 plus R over N, you'll notice that that is exactly what I have, right? And the N with M, right? That is exactly what I have here. right? So the thing is, we know how to add that up. This is going to add up to big R times A times 1 minus the R part to the mth power over 1 minus 1 plus R over N, right? That's what we get from sum of geometric series formula. Okay, now I'm going to clean this up a bit and change notations to be more of what the conventional notation would look like. So what happens is I have 1 minus 1, so that's gone. So now I have R times 1 minus 1 plus R over N to the M over minus R over N. It's kind of weird to have that minus in the bottom. So what I'm going to do is I'm going to multiply by minus 1 over minus 1. And so what I can do is turn the guys in the parentheses around, 1 plus R over N to the M minus 1 all over R over N. So we have that. Change of notation. So very common in finance books and accounting books and things of that sort. Your R, they would call it payments instead, PMT. I'm going to change the M back to N times T. And so we end up with this formula. Future value equals PMT times 1 plus R over N to the N times T minus 1 all over R over N. And this formula is important. This one you guys have to know, right? Which is crazy. It's a like what the heck? Okay, so it's a very monstrous formula. However, you know the logic that gets you to it. Didn't fall out of thin air. This is where it comes from. So this is called, let's put it down here. The future value of annuities formula. So you're making regular payments and it's being compounded. How much would you have at some point in the future? Use this formula. If you do use the built-in function in Excel to do this kind of thing, this is the formula that Excel would use. All right. And yes, the usual retort, well, if I can just put it in Excel, I don't need to know about the formula. We'll talk about that, okay? Again, do not think of any knowledge, whether in this class or any of your classes, do not think of any knowledge as useless. The more knowledge you're able to use, the better life you would live. And I'll talk about that in a little bit as well. But this is where the formula comes from. This is what it means. This is what Excel is doing in the background if you try to enter the future values of annuities formula in Excel. Now, here's something else. We can change the subject of the formula, which sometimes we want to do. To PMT. So I can solve for the payment. And of course, by multiplying and dividing, we can get the following. So it's going to be the future value times R over N divided by 1 plus R over N to the NT minus 1. This is also a formula that you should know, but it's really the same as the previous formula, just solving for the other thing. This is called the sinking fund formula. Okay, and basically, this is a sinking fund where a sinking fund is something, I'll talk about this more tomorrow. A sinking fund is like a fund that you use to save up for something in the future. So if you're putting money into an account regularly, being hit with interest to save for something in the future, and you want to know what payments should I be making to get that future value that I'm hoping for, you'd use this formula instead. So that's called the sinking fund formula. We'll do an example with this tomorrow. Today, I just want us to use the future values of annuities formula. So we're going to do one example, but we're going to get a lot of mileage out of that example. I'm going to rant about the results of that example for a little bit. Then I'll let you guys go. That's hopefully that sounds good. Let's even if it doesn't, that's what we're doing. It's my class. Okay. All right. Let's get to it. I typed up some of the examples. So 3 examples is all I want to do for this section. We are going to do 2 of them today, but this one is just a small, it's all just modifying this first example. Okay, so here is the first example. And obviously at this point, you'll notice that this is kind of more realistic than what we've been doing. So let's actually see how to deal with a problem like this one, right? Which is obviously a problem you'll need to know how to solve on a test or whatever. Okay, you deposit $1,000 a month into an account. It's being compounded monthly at 4% APR. How much money would you have after 40 years, right? So you don't just throw in $1,000 and then walk away. You come back every month. You get paid every month. You come and you deposit $1,000 into this account, right? Which, I mean, you guys have a business degree from Fordham. You should be able to do this without affecting your life too much after a couple years out of college. You got a good job. Hopefully everyone is able to do this because what's going to happen is going to be amazing. And hopefully you guys find it amazing. So let's say you're able to do this, right? Religiously. Every time you get a paycheck, you do an automatic withdrawal. Withdraw $1,000 out of whatever you get paid at the end of every month, maybe $500 from each paycheck. And you just deposit it into an account that's growing 4%, which is not hard to get. The stock market on average returns 8 to 10% before taxes. And so if you're smart with your taxes, you can get away with growing more than 4%. People who are very smart with their money and taxes and know about stuff that I'm telling you guys to know about, and don't just let their calculators do the thinking for them, they're able to get 7 to 8% usually. So 4% is actually quite modest. It's very doable. So let's say you're very dedicated, you're very, you're on top of things. This happens without you knowing. You set it automatically to deposit money, right? So this is going on your entire working life, right? So, and then you do whatever else you want with the rest of your money, right? Invest in Bitcoin or cryptocurrency or something. It doesn't matter. Do whatever else you want, but this is happening. And you keep this up for 40 years. How much money are you going to have at the end of that time period? Well, for something like this, we need the future value of annuities formula because you're making regular payments. How much do you end up in the future? So here, what we have is we're making payments of $1,000. We are getting 4% interest on these $1,000. It's being compounded 12 times per year. I'm keeping this up for 40 years, right? And so, right, so from you're around 20 to around 60, about the time when you're retiring, hopefully, you get these are the values. So this means how much would you have at the end of 40 years? No one wants to calculate adding up all these for 40 years and doing all the things. And even with an Excel drag and drop function, it's still kind of annoying. You would use the FV function in Excel, but let's do it by hand. So we know FV is going to be payments times 1 plus R over N to the NT minus 1 over R over N. Keep writing down the formulas until we remember it. Now we're going to plug that in. So we have 1,000, 1 plus 0.04 over 12, 12 times 40, right? So this is happening around 480 times. And it's being hit with compound interest those times. So we end up with that. And now let's actually make sure that we know how to compute this in your calculators. So let me know what that is quickly. What do you guys get? Come on, someone tell me.
I don't know why I keep getting 0 every time I plug it in.
Okay, so that means you're plugging in something wrong. You need to make sure you're
Yeah.
checking your parentheses or something. Anyone else get a number? It's definitely not 0. Yeah.
I got
Yeah.
yeah, I got 1,181,961.
How many cents?
34 cents.
Yeah, that sounds about right. That's what you should get. And please, people, try it. Begging you to participate. Yeah, you don't want to find out on the test that you don't know how to use your calculator. You want to find out now so that you learn by the time the test comes around. Okay, so that's how much. And as I mentioned, that's very realistic. It's pretty much, dare I say, as sure as almost anything else, a surefire way to become a millionaire. Invest your money in the stock market, like $1,000 a month, you're a millionaire, right? You can do more than that. You end up multi-millionaire with very little effort on your part. Just partner with $1,000, and hopefully you make enough money that you can do that every month without missing it. And you forget about it, and you essentially, yeah, you can do whatever else you want with your life, right? Become an artist, chase your dreams, invest in risky investments. Even if nothing else works out in your life and you keep this thing going, you end up a millionaire at the end of retirement, right? So not bad, right? You'd be in a better position than a lot of people just by doing this, right? Very realistic to actually get done. And yeah, you're a millionaire with just $1,000 a month. Now, let's elaborate on this example for a little bit. If I were to ask this question, let's do this question right now. How much of this final sum is from interest? Let's figure that out. Yeah, so tell me, how would you actually figure that out? If I want to know how much of that did I get from interest, how would I figure that out? Just give me the concept here. How do I figure out how much is from interest? Come on, make a guess. Anybody? Tell me what you're thinking.
Can you just multiply it by the APR or divide it?
Multiply what by the APR?
The final dollar value.
Well, no, I mean the APR is already factored in to this figure, right? We're already doing the interest here, right? So this includes interest already, right? So interest is not something we have to calculate here. It's already been calculated, right? So that's the total sum. So how much of that is interest? How would I figure out how much of that was gained from interest?
Wouldn't it just be 4% of the final solution?
4% is the APR, and it's being compounded, remember, so it's not simple interest. So yeah, no. It's even simpler. You don't need to multiplication doesn't come into the solution. At least not in the general concept. There's going to be a point where we multiply, but for a different reason. What do you guys think? I mean, we understand how interest works. Like you put money in a bank and they give you interest. So let's make it a little bit easier. I go to a bank, I put in $1,000, right? And I do nothing. The next month, this is never going to happen in a bank, but just go with me here. The next month, I look at my bank account and now I have $1,002. How much of that sum is interest? Right? Put in $1,000 in the bank. I do nothing. I come back, look at my account. Now it has $1,002. How much interest was paid on the account?
Would you not just do oh no, because it's compounded. I was gonna say, can you not do 1,000 times 40 and then subtract that?
No, you're doing way too complicated. Like with this example, right? I put $1,000. I look at the end at the future value. It's 1,002. How much of that 1,002 is interest?
The $2.
The $2. The $2 is the interest, right? Because that's the thing that they paid you for giving them your money, right? The interest is the fee that they give you for giving them your money. How do you come up with $2? What did you do?
Well, I just know that we started with $1,000, and if it's been a month and we hadn't deposited anything more, then the $2 has to be what they gave us for interest.
Yeah, but how did you come up with the number 2?
Oh, it's what the interest is, like 0.02%.
Right, but I mean, I asked the question. I put in 1,000. I saw 1,002, and you told me $2 is from interest. What did you do in your brain to get that calculation? How did you come up with 2?
Oh, like 1,002 subtracting what my initial.
You subtract, right? It's a subtraction. It's not like multiplying or dividing anything or the APR. Like you don't need to know that. It's much simpler. You just subtract. What is the total now? Subtract how much money I actually put in. The rest of it is interest. Interest is the part that I don't put in, right? So this is going to just be the total minus what we put in. You guys are thinking too complicated, right? So I know we have a lot of formulas, but you use them when you have to use them. You don't use them just randomly, right? That's how you find interest. Whatever, I know how much money I put in, so any extra is interest. How do I find the extra? Just subtract, right? Take the total, subtract what we put in, right? Now, to figure out what we put in, multiplication is going to come in there, and I think that's what who was talking earlier? Stephen, I think that's what Stephen was getting at when he started talking about, you know, the 480, blah, blah, blah. But yeah, we have the total minus, how do I figure out how much I put in?
You just multiply 1,000 times 12.
Yeah.
And then you multiply that by 40.
By 40, right. You're putting $1,000 12 times a year for every year. So you just multiply there, right? So that's how much money we put in. Now that I think it's 480,000, right? Yeah. So this is what we put in. Okay. Now here's what's cool and I'm going to show you what's really cool about this. And this is, again, just going to add to the mystery of compound interest that I've kind of been harping on. So if you do this exercise, you would have actually deposited $480,000 over these 40 years. If you subtract these, you would get, and I did the calculations here, I think, and you guys can check my math on this, 701,691 and 34 cents. That's from interest. Okay. Now, unlike in my 1002 example, what do you notice about this interest? Anything jumps out at you about this interest? Anything strikes you about the number 700,000?
It's more than what we initially put in.
It's more money than you actually put in. Okay. Now, when you hear people use the catchphrase, oh, get your money to work for you, this is what they're talking about. You've worked and you're able to produce 480,000. Your money gets put to work. It produced 700,000. Your money works harder than you do, pretty much, right? You're not going to become a 4% better person year upon year. Your money can get 4% better year upon year. And when it's compounded, it gave us an extra 700,000 in this scenario. So we've actually gained more in interest, not from our efforts, not from us doing any extra work, not from anything, just on interest, us putting in our money and forgetting about it. Our money grows more, almost twice as much as we put in. Okay, so that's the first thing, but it's going to get cooler. So again, this goes back to my example when I was saying, oh, how billionaires can give away millions of dollars, yet they end up richer the following year. It's because their money's working for them the whole time. So they're making even more money than they're actually putting in to their fortune, which is crazy. And it seems counterintuitive, but when you see the math, you start to understand why this is happening. Okay. Now, here is what I want us to do. And there's going to be a reason why I want to do this, but I want to do this last example right here. And then I'll talk about it a little bit. Please don't be shy. When you guys take a long time to give your thoughts, it drags out the class time even more. Because I'm just going to wait for you guys to say something. Because I know that's how you learn better, and that's how you're going to perform better. Okay, so suppose we did 2% instead. So instead of 4%, all the same numbers, but it's 2%. Right, so you have your payment is 1,000. You have your interest rate is 2% this time. N is still 12. Time is still 40. Right, nothing changes about the situation other than the interest rate. So this means that your future value is going to be. Let's write out the formula every time so we make sure that we remember it. So in this case, it's going to be 1,000, open parentheses, 1 plus R over N, close parentheses. You're going to put that caret. Then you're going to open parentheses. You're going to put in 12 times 40. You're going to close parentheses. You're going to subtract 1. You're going to close parentheses again. And you can press equal at this point, then the division sign. If you want to do everything all at once, you would actually need another parentheses here, then a division sign, then an open parentheses, and put the R over N in here, if you're using a calculator, by the way. And then over, you open parentheses, you put in the, and I'm not putting R over N, I'm putting 0.02 over 12, and then 0.02 over 12. Now, I don't want you to wait 5 minutes for you guys to answer me here, so I'll actually tell you what the answer is going to be this time around. I believe, and you guys can double check my calculations on this. The result this time is 734,000. $435.62. Just a drop in 2% made a huge difference, didn't it? Right? We went from being a millionaire to having 700,000. Still a nice chunk of change. It's definitely better than the guy saving his money in his checking account. He's going to retire with 480,000. Those of us who pay attention in class and know about the power of compound interest and invest our money wisely, we're going to end up millionaires. Someone who invests their money with compound interest but didn't do it as wisely, made 2%, they didn't make a millionaire, but they still ended up better than the guy saving his money under his mattress, okay? That's not the whole point of this example. Let's actually flesh out some more. Here's something else I want you to note about this. If I take the 734, 435.62 over the 1181, 961.34, you'll notice that this is around 62%. In other words, you made about 62% of what you could have made with a slightly higher interest rate. Now, it actually goes further. This also means you made 1/3 of the gain that you could have made at 4%. Okay, and you can do those calculations on your own. I'm not going to do it for you here. So the extra that you get in interest, it's actually 2/3 more than the extra you would get from interest in the 2% scenario. And here's why I'm doing this. Now, these numbers I chose them to be somewhat realistic. Getting 4% compounded interest on your money should be doable. It's not anything crazy. Like I said, you put your money in the stock market wisely, you're getting 8 to 10% compounded before taxes, pretty much with no work at all. So getting 4% is very doable, right? If you're not smart with how you're paying your taxes and you don't do your taxes well, and maybe you make some other mistakes, and let's say you get a 2% return, it drops your return drastically. But that's not the only thing I want you to get from this. There are a couple more things I want you to appreciate here. Note, in 2015, it's around the same now, but in 2015, the average fee for money management is it's going to be around the same, was around 2.74%, right? So again, to kind of reiterate the importance of what I'm talking about. A lot of you think, I don't need to know this formula and all these calculations because I'm just going to use my calculator or Excel, or better yet, I'll just hire someone to do my finances for me. Okay, so let's say you could have made 4%. You go and hire someone to manage your money for you, and they're like, I'll charge you a 2% fee. Now you, not knowing about compound interest, are like, that doesn't sound very much. So you're telling me I'll give you $100, you're going to make me rich, and all I have to pay you is $2 out of that $100? And he's like, yeah. And you're going to be like, sign me up. That sounds great. Because you don't know about compound interest. You didn't pay attention in class. What actually happens from that decision? This is what happens. Instead of being a millionaire, you are going to be here. Now, on top of that, what else happens? Well, you made 1/3 of the gain that you could have made. However, remember, where is the extra 2% going? Well, to the person that you paid to manage your money, which means where did the extra 2/3% of gain go? Well, to your fees, of course. Your financial advisor got that extra 2/3 growth. So here's what actually happened. Because you didn't understand compound interest, you decided to pay someone 2% compounded over 40 years. At the end of the day, that person who didn't work for that hard-earned $1,000 that you put in actually gained 2/3 of the work that your money did. and you only gained 1/3, right? Your financial advisor actually makes out more than you. And on the face of it, it doesn't seem like he would, because he only makes 2%. So the 2% is the other thing I want to make sure you get. 2% is a lot. It's expensive. It doesn't sound like a lot, but it is. And so you guys might have watched Shark Tank and things of that sort, where people will be offering stuff and they'll be arguing over the minuscule percentages, right? So a shark will say, I'll give you this much money for this much stake, and you get 8% royalties. And then the person will counter with, okay, I'll take that deal if you can bump it up to 8.25% royalties. And people who don't know about compound interest is like, why is this guy even fighting about 0.25%? This is why. It's the difference between being a millionaire and not, because it's compounded over years. They understand these small percentages aren't really small. Compound interest makes things grow a lot faster than you would think. And so, yeah, fighting over that 0.25% is worth your time, because you are literally giving away a lot of your fortune by not fighting. So we'll end right there. I think that's all I want to do today. And of course, we went over time because no one was responding to me. But hopefully you found that enlightening, and you'll think more about the future, about paying attention to your math and paying someone else to do your work for you, or just letting the calculator do it and not really understanding. But we'll stop there. I'll leave this example for you guys to try for tomorrow. So try this and let me know what you get. But we will wrap up there. Thank you for your attention. Hopefully that was helpful. And I think we will end there. So, oh, there's a chat in the private. Look at, I think you mean test. Look in the syllabus. It's the dates are all in the syllabus. They're actually in red in the topics list. Okay, so we will end right there. Hopefully you had a good weekend. Have a good rest of your day, and I will see you guys in the next one. Ciao.